the continuation of previous video. So here this is a closed loop control system. As you can see, a closed loop control system. Now the closed loop transfer function C of s divided by R of s is equal to G of s divided by 1 plus G of s into H of s. So the pole of this closed loop transfer function is nothing but this term, or it also can be considered as zeros of this. When you are considering poles, so whatever the denominator term, you have to equate to 0 and you have to find it, factorize and equate to 0. The same effect will happen. You are considering this term and it's 0. That means again it's a numerator, you have to equate into 0. Both are same. So when you are coming in the closed loop stability, a system is said to be closed loop stable or simply stable if the poles of the closed loop transfer function, that means what I told here, poles of the closed loop transfer function, that is the zeros of 1 plus G of s into H of s are all in the left half of the S-plane. Exceptions to the above definitions are system with the poles or zeros intentionally placed at S is equal to 0. Now, Nyquist, we already seen that Nyquist stability criterion is based on principle of argument. So we are going to see the principle of argument. What is meant by principle of argument? Now consider a function q of s that can be expressed as a quotient of two polynomials. That means it is a numerator denominator term. Okay, quotients of two polynomials, division of one polynomial by other polynomial, that is known as quotient of two polynomials. Q of s is nothing but quotient and remainder. So quotient of two polynomials. Each polynomial may be assumed to be known in the form of product of linear factors indicated as follows. So this is a polynomial, but it is expressed as a product of linear factors. So you can see here s minus alpha 1, s minus alpha 2, s minus alpha m, like that, the numerator polynomial, and second polynomial is s minus beta 1, s minus beta 2, s minus beta n. Now, normally alpha 1 represents the zeros and beta 1 represents the poles. Now, let s be the complex variable represented by s is equal to sigma plus j omega on the complex S-plane. Then the function q of s, this q of s is also a complex, because you know that it is also complex and may be defined as q of s is, we are using as u plus jv, and represented on the complex qs plane with the coordinators u and v. So the function q of s, that is represented on a complex QoS plane with the coordinates are u and v. Now equation 8.1 indicates, this equation indicates that every point s in the S plane at which q of s is analytic. So here this 8.1 indicates that for every point s in the S plane at which q of s is analytic. So here a function q of s is said to be analytic in the S plane provided the function and all its derivative exist. So when you are telling it as analytic, so So here, what is the required conditions? 8 point indicates that for every point S in the S plane, so here you are having the S plane, this is sigma, no, here this is sigma, this is j omega, this is S plane. Now here you are having QS plane with here a U and here JV. So this is Q of S plane. Now what is the here? The expression this indicates that for every point S in the S plane, every point S in S plane, okay, S in S plane, at which Q of S is analytic. That means a function Q of S is said to be analytic in the S plane provided the function and all its derivative exist. That means function and its all derivative exist, then we can call that function as analytic. Now the point in the S plane where the function or its derivative does not exist are called singular points. The point on S plane, point on the S plane in the S plane where the function or its derivative, function or derivatives does not exist are called singular points. So our concern is non-singular points, that is function and its derivative exist. But if that is not exist, then it is known as singular point. Now we can find the corresponding point Q of S in the QS plane. So suppose if there is a point in S plane, we can find the corresponding point in QS plane. Okay, we can find the corresponding point QS in the QS plane. Alternately, it can be stated that the function Q of S maps the point in the S plane. Function Q of S maps the points in the S plane into the Q of S plane. It maps. We can say that it can be stated that the function Q of S maps the point in the S plane into the QS plane. Since any number of points in the S plane can be mapped into QS plane, it follows that for a contour in the S plane which does not go through any singular point, there corresponds a contour in the QS plane. So here, if a contour in the S plane, okay, there correspond to a contour on the QS plane. Okay, so a contour in the S plane that is non-singular points. Singular points means Q of S or its derivative does not exist. So a point on the, so we can say that contour in the S plane which does not go through any singular point, there correspond a contour in the QS plane. Okay, so here this is an example. Here you can see an S plane, arbitrarily chosen S plane contour. This is an arbitrarily chosen S plane contour. Here S1, S2, S3, S4, S5, and it is in direction is represented in clockwise directions. Now when you are representing it into the QS plane, so how it can be represented? So here, what it is, a region to the right of the closed contour is considered enclosed by the contour when contour is transferred in the clockwise direction. So here the contour is in clockwise direction. So region to the right, region to the region to the right of the closed contour is considered enclosed by the contour when the contour is traversed in the clockwise direction. So how it is happening is, for example, I will explain this. For here, after S1, it is in clockwise direction. You can see one arrow here. So S1, S2, S3, S4, S4, like that. Now this is the corresponding QS plane contour. So the angle normally, positive angle is in counterclockwise directions. Okay. So you have to take counterclockwise way of representation. First, if you are considering S1 to the right of S1, so we marked corresponding QS1 here. Okay. And the portions right of S1, that is S2, that is you are in a positive direction. Positive direction means a positive angle, that means in counterclockwise directions, that is Q of S2. After S2, you can see that S3. So you have to go positively. So Q of S3. After S3, right of it is S4. Then next is Q of S4. Like that, the contour is forming. So there is no particular shape. Okay. There are some points that will come, we will see in the next page, but there should not be any particular shape. Now, while developing the Nyquist criterion, we are not interested in the exact shape of the QS plane contour. We are not interested. Then what we interested? An important fact that concerns us is the encirclement of the origin by the QS plane contour. For example, how much time it this is the origin. How much time it encircles. You are not bothered about its shape. So here you can see it encircled 2 times. Here also. But when you are coming here, it encircles only 1 time. So our concern is not the shape of QS plane contour. Our concern is how much time it encircles the origin. An important fact that concerns us too is the encircle. So, important fact that concerns us is the encirclement of the origin